There is a small organ behind your breastbone that helps build the cells protecting you from viruses, cancer, and even your own immune system. But shortly after puberty, it begins to shrink. Healthy tissue is gradually replaced by fat. Its ability to produce fresh immune cells falls. By old age, much of the organ can become difficult to distinguish from the tissue surrounding it. That organ is the thymus. For decades, scientists treated this disappearance as an unavoidable part of growing older. Now researchers are asking a much more provocative question. What if the thymus could be rebuilt? The idea matters because the thymus is not just another gland. It is where developing T cells go through one of the most demanding training programs in the human body. T cells begin as immature cells produced from precursors in the bone marrow. They travel to the thymus where they are tested. The first test asks whether they can recognize signals presented by the body's cells. A T cell that cannot do this is useless and is removed. The second test is even more important. The thymus exposes developing T cells to proteins normally found throughout the body. Cells that react too aggressively against those proteins are destroyed or redirected. In simple terms, the thymus teaches immune cells two lessons. Attack what does not belong. Do not attack what does. Only a small fraction of developing T cells pass both tests. The survivors leave the thymus and circulate through the blood, lymph nodes, and tissues, ready to respond to infections and abnormal cells. During childhood, this system is highly active. The thymus continuously supplies the immune system with a diverse population of young, flexible T cells. Then the organ begins to change. Its working tissue contracts. Fat and connective tissue move in. The production of new T cells declines. The immune system does not suddenly stop working. Adults retain many of the T cells created earlier in life, and those cells can multiply when needed. But the collection becomes older and less diverse. Imagine a security team that keeps copying its existing workers but recruits fewer new trainees. The experienced guards may remember familiar threats, but the team becomes less prepared for something it has never seen before. That is one reason older adults can respond less effectively to new infections and some vaccines. It may also help explain why immune aging is associated with cancer, chronic inflammation, and reduced recovery after treatments that damage immune cells. The thymus does not simply get smaller after puberty and then remain stable. Its capacity continues declining across adulthood. This makes it unusual. Many organs lose function gradually, but the thymus begins retreating while the rest of the body is still young. In 1961, immunologist Jacques Miller demonstrated the organ's importance by removing it from newborn mice. The animals developed severe immune defects. Until then, many scientists had considered the thymus an evolutionary leftover with no major purpose. More than 6 decades later, researchers are now investigating whether restoring this once-dismissed organ could rejuvenate part of the immune system. The first approach is not to build a new organ. It is to persuade the old one to grow again. The thymus has a limited natural ability to regenerate after injury. Following chemotherapy, radiation, severe infection, or other forms of stress, it can partially recover. Scientists have identified signals involved in that repair process. One of them is RANKL, a protein that communicates with cells inside the thymic environment. In preclinical experiments, researchers found that stimulating this pathway could restore aspects of thymic structure and function in older mice. The treatment increased the production of new T cells and improved immune recovery. This is important because it suggests the aged thymus is not necessarily dead. Some of its regenerative machinery may still exist. The problem could be that the repair signals are too weak, incomplete, or poorly coordinated. Other research has identified interactions among specialized epithelial cells, fibroblasts, immune cells, and blood vessel cells that help the thymus recover after damage. The organ is less like a bag that produces T cells and more like a carefully organized school. The building matters. The teachers matter. The classrooms, chemical signals, and supporting cells all matter. Simply delivering more immature immune cells would not solve the problem if the environment required to educate them has collapsed. This is where the second strategy becomes more ambitious. Instead of repairing an old thymus, scientists want to grow replacement thymic tissue from stem cells. In 2026, researchers reviewing the field argued that advances in single-cell biology and stem cell engineering have brought this idea closer to reality. The goal is to begin with induced pluripotent stem cells. These are adult cells that have been reprogrammed into a state resembling embryonic stem cells. In theory, they can then be guided to become thymic epithelial cells, the specialized cells that help train developing T cells. A patient's own cells might eventually be used to create compatible thymic tissue. This could reduce the problem of immune rejection and allow the new tissue to educate T cells using that patient's genetic identity. The potential applications extend far beyond normal aging. Some children are born without a functioning thymus because of rare developmental disorders. The current replacement option can involve transplanted thymus tissue from donors, but donor material is limited and biological matching remains difficult. Patients receiving chemotherapy or bone marrow transplantation can also lose large numbers of immune cells. Rebuilding the thymus might help them produce a fresh T-cell population more efficiently. Cancer treatment is another possibility. Modern immunotherapies often depend on functional T cells. A regenerated thymus might improve the supply and diversity of those cells, although that remains an experimental idea. Researchers are also interested in autoimmune disease. Because the thymus helps eliminate T cells that attack the body, restoring accurate immune education could theoretically improve tolerance. But this would require extraordinary precision. A poorly constructed thymus could create the opposite effect. It might release cells that fail to recognize infections or cells that attack healthy tissue. That is the central challenge. Building something shaped like a thymus is not enough. It must perform selection correctly. Millions of immature cells enter this system, and most are intentionally destroyed. The organ must preserve useful cells while removing dangerous ones. A mistake in either direction could produce immunodeficiency or autoimmunity. There is another complication. Researchers still do not know whether thymic decline is mainly a cause of immune aging or partly a response to it. Restoring the thymus might improve the production of naive T cells, but older bone marrow may still provide fewer or less functional precursor cells. Chronic inflammation may continue damaging the new tissue. Other aging organs may still send harmful signals. The immune system is a network. Repairing one node may help, but it may not reset the entire system. This is why claims that thymus regeneration has already reversed human aging deserve caution. A small 2019 pilot study tested a combination that included growth hormone and reported signs of thymic regeneration and changes in biological age measurements in a small group of men. The study was intriguing, but it was not a large randomized trial. It combined several interventions, had no conventional placebo-controlled design, and was too small to establish that the treatment slowed aging or extended life. Growth hormone also carries risks and should not be used as a do-it-yourself longevity treatment. Higher exposure can affect blood sugar, fluid retention, joints, organs, and potentially cancer-related pathways. No approved therapy currently regrows the thymus to make healthy people younger or extend their lifespan. The most advanced ideas remain experimental. That distinction matters because the thymus has become attractive to the longevity industry. An organ that visibly shrinks with age creates a powerful story. If aging makes it disappear, restoring it sounds like turning back the clock. But biology is rarely that simple. The thymus begins shrinking during a period when humans are still physically strong and reproductively mature. Some researchers think this process might have evolved partly to reduce the enormous energy cost or autoimmune risk of continuously generating new T cells. If that is true, completely restoring youthful thymic activity may involve trade-offs scientists do not yet understand. More immune activity is not automatically better. An effective immune system needs strength, restraint, memory, and diversity. The real goal would not be to produce the maximum number of T cells. It would be to rebuild balanced immune function. Still, recent research has changed the thymus from an organ scientists mostly observed into one they are actively trying to engineer. They are mapping its cells one by one. They are identifying the signals that trigger natural repair. They are testing ways to grow thymic epithelial cells from stem cells. And they are studying adults who lost or had their thymus removed to understand how much this organ continues to matter later in life. The deepest lesson may not be that the thymus holds the single key to longevity. It is that a part of aging once considered irreversible may contain hidden regenerative capacity. The organ does not vanish completely. Fragments remain. Supporting cells remain. Repair pathways remain. The old immune school may be nearly empty, but parts of the building are still standing. The next challenge is to discover whether scientists can reopen it without teaching the wrong lessons. For people today, there is no supplement, injection, breathing exercise, or diet proven to regrow the thymus and reverse immune aging. The practical ways to support immune health remain less dramatic. Vaccination when appropriate, regular physical activity, adequate sleep, sufficient nutrition, avoiding smoking, managing chronic illness, and discussing unusual infections or immune problems with a clinician. For science, however, the thymus represents something larger. A small organ that was once dismissed as useless helped reveal how the immune system works. Now, the same organ may help answer one of the most important questions in aging research. Can an old body be persuaded to build young immune cells again?